Homework 5, problem 3, find the potential V everywhere inside the box, where the box has 5 of the sides at potential V equals 0 and 1 of the sides at a potential V equals V naught. Again, we're going to use separation of variables to solve this problem. To go through, it's not going to be in order to use separation of variables, we have to explicitly write down what the problem is. The first thing that we're going to write down is we are solving Laplace's equation, so that's minus del squared of V must be 0. The second, I want to write down what the boundary conditions are. We're going to define that the size of this cube has size A everywhere. And so the boundary conditions on 5 of the sides, we're going to find that V at, let's see, this I believe in coordinates is going to be x, y, and z. So V at x equals to A is V at x equals to 0, which is V at y equals to A, which is V at y equals to 0, which is 0. And so these are kind of the uninteresting ones. It says I'm 0 on my 2 limits in the x direction, I'm 0 on my 2 limits in the y direction. For the interesting one, I of course have V at z equals 0 should be 0, and V at z equals A should be some non-zero value V naught. As I go forward with this, we want to employ the big idea in separation of variables, which is that my solution to Laplace's equation of multiple variables can be written as a product of solutions in each coordinate. And so our standard here is to write that with a capital letter for the name of the function that depends only on the lowercase letter for each coordinate. We're going to use Cartesian coordinates, so it's capital X, capital Y, and capital Z, little z. And so this is an assumption to the problem. There's no proof of this. This is an assumption to start the problem. When you take this assumption, plug it in here, what we're going to find is we get the following 3 differential equations. The second partial derivative of capital X with respect to x is Cx capital X. Same thing for y. And the same thing for z. Oops. Okay. With the caveat that these 3 constants, Cx, Cy, and Cz, have to add up to 0. So Cx plus Cy plus Cz must add up to 0. Now, similar to the first problem, because I have 0 boundary conditions on both ends of my x and y coordinates, I know that they're going to be, the only interesting solutions there will be sines and cosines, and so that's going to force Cx and Cy to both be negative. And so we're going to make the assumption that Cx is going to be minus kx squared, that Cy is going to be minus ky squared, which of course is going to force Cz to be positive. And so without loss of generality, we can define Cz to be positive kz squared, which is going to be equal to kx squared plus ky squared. Okay. Rewriting the differential equation with this in it, we're going to get the second derivative of x. Now I'm going to explicitly write the x in here. It is minus kx times x respect to x. The solution here is, of course, sines and cosines, a linear combination of sines and cosines. The boundary condition, when I apply the boundary condition, the first boundary condition is that V of R at x equals 0 should be equal to 0. That's going to translate to whatever the y and whatever the z are. If they're interesting, if they're not always 0, then the boundary condition will be completely specified by this x function. The x function at x equals 0 will only be b, right? Because cosine of 0 is 1, sine of 0 is 0, so that goes away. That's 1, so it's just b. This must be equal to 0, which is going to give us the boundary condition, of course, that b equals 0. The second boundary condition, v of r at x equal to a equal to 0. This again is going to simplify. This is y v of z times now a sine of kx x, which is going to give us a condition on kx. This will only equal 0, equals 0. This will only equal 0 if the sine equals 0. So that's going to actually give us a condition on this kx. That condition is going to be that kx must equal n pi over a for n positive integers. So continuing on with the problem from here, it's good now just to write what our capital X is. Our capital X of x in this case is going to be some unknown constant a times the sine of n pi over a times x. Now, I'm a big fan of using symmetry in order to do this stuff. I see that the y conditions, the conditions that we had for y here, and our boundary conditions there, are identical to what we had for x. We have the same idea that the cy has to be negative, we have the same boundary conditions, and we have the same form of the differential equation. So without having to go through any of the work again, simply by symmetry, I can write that my solution y has to look very, very similar. I'm going to write this a prime, sine, and then I'm going to do an n prime pi over a y. Okay, where the constant a and a prime can be different, and my integers n and n prime can be different. Okay, but I didn't have to do any more work in order to find those. Now we can look at the z differential equation. The z differential equation, I'm going to, for simplicity, I now even know what this kz looks like. This kz is the square root of n pi over a squared plus n prime pi over a squared. Okay? But for simplicity, I'm not going to actually write any of this down. I'm going to leave it as kz just because it's easier to do the algebra if I leave it as kz. The differential equation is, of course, this second derivative of z is a positive kz squared times z. The result of this could be positive and negative exponentials, which let's go ahead and work with that. So let's do this. Let's say that z of z is going to be d e to the positive k zz plus e to the exponential of negative kz z. Okay, so that's our condition. That's the solution, the general solution for z. Now we're going to look at the first zero boundary condition for z and see what we get. And so the first zero boundary condition, the first zero boundary condition is that v at z equals 0 is 0. For us, that's going to be x, y, which I'm not writing them out explicitly because I don't need to, and then this thing, d e to the kz, which is just 1, plus e e to the minus kz0, which is again 1, this has to equal to 0. Well, this will only equal 0 if e is negative d. Okay, so that solves for e in terms of d. And so I can write down what z would look like here. Z is going to look like d times exponential of positive kzz minus exponential of negative kzz. But I recognize that this is simply twice the sinh. Okay, and so I'm going to write this as d. I'm going to absorb this 2 into that d times the sinh of kzz. I could have also started with sinh and cosh and eliminated the cosh as an option whenever solving this, but this is just one way of doing it. So now I know what z looks like here. At this point, it's actually useful for us to write down what the full solution looks like. The full solution is going to look like the v of r is going to now be equal to, I'm going to leave some space, and I can, when I multiply this x times this y times this z, I notice that I have 3 constants. I can absorb them all together just to some overall a. And I'm going to get the sine of n pi over a x times the sine of n prime pi over a y times the sinh of kz, where again we know what kz is, but out of laziness I'm just going to leave it for kz for now. So we're pretty much done except for one part. We have these n and these n primes, and we have a valid solution for every single one of them. So properly I need to sum separately over n and n prime, and I can have a different constant for each n and n prime. And so this is the general form of the solution to Laplace's equation. So wink, this is the general form of the solution to Laplace's equation that satisfies these 5 boundary conditions. The 6 boundary conditions will specify what all of those a sub n, n primes are. So go ahead and do that. This is evaluated at z equal to a, and so the last boundary condition, okay, is evaluated v at z equal to a is some constant v naught. For us, we can rewrite this as this is the sum over n and the sum over n prime, capital A and n prime. We have the sine. We have another sine. And we have a sinh, and our sinh is evaluated at kZA. Okay. And this should be equal to positive V naught, and so just a constant. Okay. We're going to use the same Fourier analysis that we used on for all of these Cartesian separation of variable problems. And we're going to use the same trick, but now we have to use it for both in the x and the y direction. And so that trick, if you remember, is we multiply by sine of m pi over a x, and then add an integral dx from 0 to a. We're going to do that also, right, with the sine of m prime pi over a y, and add integral and integrate dy from 0 to a. And then we're also going to use this trick, right, that this, the orthogonality. Orthogonality. The integral dx from 0 to a of sine of n pi over a x sine of m pi over a x is equal to 0 for n not equal to m, and equal to a over 2 for n equal to m. And so even without writing the integrals on the left-hand side, since I know that I'm going to get my n's are going to go to m's, and my signs are going to be replaced with a over 2. Okay, so the left-hand side now can be written as a m prime a over 2. This is for the x. Okay. A over 2. This one's for the y. And then I still have a sinh of kza. Now this is going to be equal to, now I'm going to do this out on this side. So this will be v naught, and then I have an integral from 0 to a dx sine of m pi over a x. And I'm going to have an integral. I've put these brackets here just to help me separate stuff, from 0 to a dy sine of m prime pi over a y. Now this is the same integral. You'll notice that I can think of this x as a dummy variable, and so it's the same integral, this one with an m, this one with an m prime, and this evaluates to a over m pi 1 minus cosine of m pi. Okay, and this would be the same thing, right? But m goes to m prime. Right? So this is the same, but m goes to m prime. I'm not even going to bother writing it because it's the same thing. The other thing I'd like to point out, though, is I can look at just this underlined part, and I see that as m for odd choices of m, cosine of m pi for m odd is -1, so that's going to be 1 minus -1, or positive 2. For even choices, cosine of m pi is going to be positive 1, so that's 1 minus 1, which is going to be 0. So this will give us 2, 0, 2, 0, 2, 0. Or it's just going to be only over the m odd, and I can multiply by 2. And so that's what I'm going to go ahead and do. I'm just going to say that really for both of these, copying this down, I'm going to get a m prime is going to be equal to, I'm going to multiply both sides by, so this will be v naught a squared over 4 sinh of kza. And then here I'm going to have so a squared over 4 sinh of kza, got that. And then here I'm going to, from both of these, so I'm going to have a 2a over m pi and a 2a over m prime pi. Okay. And this was a squared on bottom and a 4 on top. Okay. So the a squareds are going to cancel. I'm going to get 4 times 2 times 2 is going to be 16. And so this is going to be 16 v naught over pi squared m prime sinh of kza. There we go. And so the final thing for us to do is to write out what our actual function is. And that's just going to stick everything together. And this is the expression, and all I'm going to do is I'm going to stick in what my solution for this a m n prime, and I'm going to make sure that my n's and n primes only go over the odd numbers. Doing that, right, I'm going to get that in order to make things look a little bit prettier, I'm going to collect, I'm going to put this sinh over that sinh, and so I'm just telling you what I'm going to do. So my v is going to be sum n equal to 1, 3, 5, dot, 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 sum n prime equals 1, 3, 5, dot, dot, dot. And then I'm going to get 16 over pi squared m prime n prime sine of m n pi over a and x times the sine of n prime pi over a y. And now I'm going to collect this sinh of kz z over sinh of kz a. And so that is the potential that we find everywhere. Now the final thing that we were supposed to do is check this somehow. And if we go back and we look at the symmetry of the problem that we started with, okay, the symmetry of the problem is we have a box where one side is, one of the 6 sides is at positive v0 and the other 5 are at 0. We know just one of the properties of the Laplace equation is that the solution in the center is the average of the solutions on a sphere surrounding that. We can misshape the sphere as long as we do it, or we can deform the sphere as long as we do it symmetrically. And so we deform it into a cube, and so the potential in the center of the sphere should be 1/6 of v0. And we were supposed to confirm that. We were supposed to look at that. And here is this expression. I've looked at this in Mathematica. And so this is the 16 over pi n prime in n prime. I don't know why there are 2 primes there. In n prime. So that's my nm here. So there's an n and an m. I have sine. At a over 2, I get m pi over 2 and m pi over 2, right? And then I have sinh. Here's my kx, right? And I'm dividing by sinh of the kz multiplied by a. So this one is at a over 2, so that's the over 2, and this one's just at a, so that's without the over 2. I'm only evaluating every other one. That's what this comma 2 means, and I find as the solution 0.166666, which is 1/6 in decimal form.